Okay, this is part 284C3M1b7C8E13C9C6D3p38d19d7b10. It's line 22 F1FA19C3M1b7C8E13C9C6D3p38d19d7b10 radio frequency over glass formula 5G Wow Seti. There's the alien radio signal. I got froggies in my throat. Okay, wires, frequency signals for long distance communications and WOW data. Keyword radio frequency over glass. And this March 15th, 2013 was when I was working on it. Today is May the 11th. So as you can see, there was a lot of data that was done in between the originals. So this is split colliding lasers, formulas from data found in this video and in the previous video. And that's the line of data there. Hertzian Dipole magnet transformer, then another line of data, and then Anthropenic heat hydrology. And then the keywords in the next several videos, we'll be talking about dissipation, Lambda, Ferrite rod. So now the keyword Lambda was from this previous video. Line of data for Hertzian Monopile Pillings. And then the next one was another line of data and Distributed Bragg Reflector formula. So the keywords Lambda plus Distributed Bragg Reflector and Dielectric mirror. So I googled tie Sci-Fi laser thin film beam splitters. The keyword for that was passive optical network part 2 to radio frequency over glass from the previous video line of data. Anthropenic heat hydrology. Then, so we finally got to the keyword of radio frequency over glass. So a quote from Wiki. In telecommunications, radio frequency over glass, RFOG, is a deep fiber network design in which the coax portion of the hybrid fiber coax HFC network is replaced by a single fiber passive optical network, or PON. Downstream and return path transmission use different wavelengths to share the same fiber. Typically 1515 nm downstream and 1310 nm or 1590/1610 nm upstream. The return path wavelength standard is expected to be 1610 nm, but early deployments have used 1590 nm. Using 1590/1610 nm for the return path allows the fiber and infrastructure to support both RFOG and a standards-based PON simultaneously operating with 14 nm downstream and 1310 return path wavelengths. The advantages: RFOG delivers the same services as an RF DOCSIS HFC network with the added benefit of improved noise performance and increased usable RF spectrum in both the downstream and return path directions. Both RFOG and HFC systems can concurrently operate out of the same head-end hub, making RFOG a good solution for node splitting and capacity increasing on an existing network. RFOG allows service providers to continue to leverage traditional HFC equipment and back-office applications with the new FTTP deployments. Cable operators can continue to rely on the existing provision and billing systems. Cable modem termination systems are platforms, head-end equipment, set-top boxes, conditional access technology, and cable modems while gaining benefits inherent with RFOG and FTTX. RFOG provides several benefits over traditional network architecture. More downstream spectrum, RFOG systems support 1 GHz and beyond, directly correlating to increased video or downstream data service support. More upstream bandwidth, RFOGs improved noise characteristics, allowing for the use of the full 5 to 42 MHz return path spectrum. Additionally, higher performance RFOG systems not only support DOCSIS 3.0 with bonding, but also enable 64 quadrature amplitude modulation QAM, upstream transmission, and a DOCSIS 3.0 bonded channel, dramatically increasing return path bandwidth. Improved operational expenses, RFOG brings the benefits of passive fiber topology. Removing active devices in the access network reduces overall power requirements as well as ongoing maintenance costs that would normally be needed for active elements such as nodes and amplifiers. Both cost savings and increased capacity for new services, revenue generating, and or competitive positioning are driving the acceptance of RFLG as a cost-effective step on the path towards 100% PON-based access network. So April 21st created a formula from the data. Radio frequency over glass, fiber network coax portion, hybrid fiber coax network, single fiber passive optical network PON, downstream return path transition, use different wavelengths, share same fiber, return path wavelength standard allows fiber infrastructure, support both RFLG and standards-based PON simultaneously, operating downstream return path wavelengths. RFLG delivers services RF DOCSIS HFC network, improved noise performance, increased usable RF spectrum, both downstream return path directions. Operates same head-end hub. RFLG solution, node splitting capacity increases existing network. Continue leverage new FTTP deployments, cable operators, cable modem termination system, platforms, head-end equipment, conditional access technology. Downstream spectrum, increased video, downstream data service support, upstream at bandwidth. RFLG's improved noise characteristics, full 5 to 42 MHz return path spectrum. Higher performance RFLG systems support DOCSIS 3.0 bonding, enables 64 quadrature amplitude modulation upstream transmission. DOCSIS 3.0 bonded channel, increasing return path bandwidth, passive fiber topology. Removing active devices access network reduces power requirements. Maintenance costs, active elements, nodes, amplifiers. Increased capacity, new services, driving acceptance, RFLG, effective step path towards PON-based access networks. The keyword passive optical network part 2 and radio frequency over glass plus implementation plus standards plus status will be in our next video. Thank you for watching.